Morning and welcome to this edition of YouTube videos. This channel is pain free Partha, and you can subscribe and share it to your friends. And today's topic is about vaporizers and principles of vaporizers. I'm not going to detail each of them, but we should know what is behind this vaporizer. That is what is my idea is all about. Whenever I talk anything on academics, I put a big salute to the legendary teacher of 2 centuries, Professor Ravi Shankar. And today I'm going to give a good salute again. And thanks to Dr. Pankaj Kundra, whom we have shared so many things and is helpful in preparing the slides. So thank you very much again. And vaporizers basic principles. Why do we need them? Why do we need them? Because anesthetic agents are liquids, and we are the persons who give drugs through the lungs. So we may need to change the liquid to gas. So you need an instrument which gives a precise concentration. Now, if you give 0.3%, it should give 0.3%. If you give 1%, it should give 1%. If you want to give 1% at a flow rate of 5 liters oxygen, it should give 1. At a flow rate of 3, it should give 1. If you keep it Ooty, it should be there. If you keep in Pondicherry, it should be there. So this is what we mean is precision vaporizers. So this is what is the same result should come from the vaporizer. That is why we need these instruments. What are the physical principles? There are vapor and gases above and below the critical temperature. What is saturated vapor pressure, which I have already told? Again, I will hint on it. Boiling point is when the saturated vapor pressure touches the atmospheric pressure. Every substance has its unique critical temperature. One temperature is there. For oxygen, something. For nitrous oxide, there is something. Above which it exists only as a gas. Even if you give so much pressure, it will not liquefy. That is what is called the critical temperature. At or below the critical temperature, if you give pressure, it will become liquid. So the above is called the vapor. Now I am telling you, here you can see here. If you give pressure here, it remains as a gas because it is above the critical temperature. If you are below the critical temperature, then if you give pressure, there is liquefaction here. This gas becomes liquid, then it called a vapor. So the same thing, if it is below the critical temperature, it is called vapor. It is above the critical temperature, it is called gas, and hence it can interchange. So interconvertible if the temperature of this becomes different. Now if you see nitrous oxide is 36.4 and oxygen is minus 118 degrees. Now we go to volumes and partial pressures. Because if you give sevoflurane, we are giving 1%. That is a volume. But what acts into the brain is the partial pressure. We give in volumes, but what matters is the partial pressure. Partial pressure by total pressure is equal to volume percentage. I am again giving another example in this. Now if you have a partial pressure of 160 divided by 760, then it is 21%. That is what is called the atmospheric oxygen. If you divide 160 by 760, 760 is the normal atmospheric pressure, in which the partial pressure exerted by the oxygen is 160. Then it is volume is 21%. Now we can also say 21% of 760 is 160. So this is what is the partial pressure and the volume percentage. Now what is a saturated vapor pressure? I have already described in this inhalation of vapor agents. Again, I will refresh. Evaporation and latent heat of vaporization. In any liquid, some molecules will lay vapor and then comes down like this. So this is called evaporation. So this needs some energy. So this energy is called latent heat. Pressures exerted by the vapor, SVP. Saturated vapor pressure is what is the number of molecules exiting and incoming should be the same. For that temperature, it is saturated vapor pressure, because if the temperature differs, the SVP differs. Now, if you give the temperature, the saturated vapor pressure increases. And if the saturated vapor pressure touches the atmospheric pressure, then it is called the boiling point. So, if the saturated vapor pressure becomes the atmospheric pressure, now you see, Desflurane is only the boiling point is 23.5. That is why we need a separate vaporizer for Desflurane. All other things, you see, this 23.5 is very close to the atmospheric pressure, so it will boil. So that is why we need a separate vaporizer, Tech 6 for Desflurane. Now we are told latent heat of vaporization of a liquid is the number of calories required to convert 1 gram of the liquid into a vapor. Now you see, cooling of what happens is, if it vaporizes, the liquid cools. Now as the temperature comes down in the liquid, the vaporization, the volatility is decreased. So it becomes less vapor. So it becomes inefficient. That is why we want some sort of temperature compensation. Now I am going back. There is a liquid. It becomes vapor. This needs some energy. It takes from it atmosphere, and the thermal energy goes into the liquid. So the liquid becomes cooler. Okay. You can also see the AC, the freon gas. If it goes and does this Joule Thomson effect, the sideways becomes chill and there are ice cubes in it. So this becomes cool. So this is heat of vaporization produced by the liquid. So we need something, some measure to avoid this problem of cooling of liquid and decrease the vaporization. Drop in vapor, because SVP depends upon the temperature of the liquid. There is something called ethyl chloride. Say I'm not going into it. Already we got told. It is to spray it evaporates, the area cools, and the cold stimulates. That is gate control theory and pain relief. The latent heats of vaporization, you see here 35, 41, but if it is methoxyfluorine, it is 58. The liquid gets cooled slow. Now, if the boiling point is what? If you supply the heat, the SVP, what is this SVP? Number of molecules coming down, number of molecules going up are the same. The SVP increases, and if it touches atmospheric pressure, and the liquid will start to boil. SVP is high, boiling point is low. More volatile, easily vaporizable. A more liquid, volatile liquid has weaker cohesive forces. So therefore, liquid which is volatile or liquid is non-volatile, the flow and splitting ratio of the vaporizer has to be considered and changed. The air is thinner, but there is a significant depression of the boiling point. So low boiling points ether may be difficult, but otherwise this compensates for that and that compensates for that, and does nothing matter. The vapor pressure is less. Less number of vapor molecules are picked up. But what partial pressure is the same. So if you go the total pressure 760 becomes, there it is 400 or 500. So the partial pressure remains the same. That is why there is not need of any problems if you go to Ooty or Kodaikanal. Now, if you take it, the boiling point of Desflurane is 23.1. So any alterations in the room temperature will lead to problems in the SVP and boiling point, and the vapor starts to boil. So we need a supplied heat to increase SVP. We go up to 2 atmosphere, and it is under pressure. Inside the vaporizer, there is under pressure. There is no need for fresh gas flow to come and pick up in a Desflurane vaporizer. It is under pressure. It is 2 atmosphere. As soon as you open, it will come out. That is because of the supplied heat which increases. So whatever be the temperature outside, it doesn't matter. That is what is the difference between the Tech 6 vaporizer and the other vaporizer. As evaporation proceeds, the temperature falls. So the cold liquid vaporization is difficult. So all vaporizer needs to be temperature compensated. What are the different methods of temperature compensation? Now this is what I told. This is a splitting ratio. This is splitting valve, vaporizing chamber and bypass chamber. Inside the vaporizing chamber, how much is coming? The fresh gas flow. This is what is called the splitting ratio. Now there is a bimetallic valve with different coefficient of thermal expansion bound together. Now if you increase the temperature or decrease the temperature, this bimetallic valve is inside the liquid. Now if the liquid gets cooled, the thing becomes like this. So more gas may enter. Or if the temperature is high, it will further close the orifice, less gas will enter. That is that is how this bimetallic valve works. But it is a source of high resistance. So we cannot do it. Draw over vaporizer. Draw over vaporizer means vaporizer is inside the circle. There is no high pressure going inside. Patient is breathing and taking the fresh gas flow through the vaporizer. So if the patient breathes through the vaporizer spontaneously, drawing over the gas, then we cannot have high resistance like this. Now you see here, this bends like this. This temperature gets cold. This bends like this. So more gas enters. That is what is called temperature compensation. There can also be temperature compensation like this. Liquid bellows. And these are all taken from the internet for academic, non-money purpose. So the liquid bellows will contract like this, and the fresh gas more will flow. The splitting ratio will change. That is what is the difference. The greatest accuracy is between 15 to 35 degrees. The thermostat does not respond 15 to 35 degrees. If the inside of the room temperature inside the operation theater is 45, then 42, very hot, then the vaporizer may not work correctly. Now there are two more terms, specific heat and thermal conductivity. Anything vaporizer should have little higher specific heat and little higher thermal conductivity required to raise the 1 gram of the temperature. What is this? This is not about fluid. This is about the construction of the vaporizer. Don't think about fluid. This is the dabba in which the vaporizer is manufactured. This should have a high specific heat and high thermal conductivity. What is thermal conductivity? Metal is high, glass is low. Now if you see here, aluminum is okay and glass is very bad in terms of thermal conductivity. Air is very bad. Steel is okay, but here you can see 0.1. Brass is slightly okay. So copper is the best thing which has got good specific heat and good thermal conductivity. That is why many of the vaporizers are made up of copper. Metal allows easily heat to be conducted in the liquid. So that is one thing, thermal conductivity. Now if we go to two things in the construction of the vaporizer. One is wicks, another is baffles. You can see the same area. If you go to a temple there will be some wooden barricades. The public will go like this, go like this, go like this, go like this. This is what is called baffles. So this will go like this, go like this, go like this, so that the possibility of vaporization is better. Another thing is wicks. Now if you have a liquid here, water. Now if you just put a gauze piece there, plain gauze piece there, and dip in the liquid for some time, what happens by capillary action? The gauze piece becomes wet. Now this gauze piece, example I'm telling, these wicks are not made up of gauze pieces. Wicks becomes wet. Now see the area of vaporization here, 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 here. This is what is the surface area of vaporization. Whenever there are problems in volatility because of temperature changes, yes, these help. You can also increase the surface area like this. See here the baffles coming here, here. By the time there are a lot of big skirts, etc. The control tile. The wick is made up of Teflon, wherein that is supported by an internal wire coil that also creates a large surface area contact with the carrier gas. At the base of the spiral, the Teflon is made to drape in the reservoir. High capillary activity. That is why this is there. So this is also useful for liquid level compensation. Now the vaporizer gives the same amount of vapored partial or the volumes of gas even if it is filled to this or filled to this. This is what is called level compensation, for which we need the surface area to be increased, for which we need wicks and baffles. Now the classification is plenum, the gas flows, high resistance. These are all modern. Draw over, patient inspires, low resistance, and EMO vaporizers, Oxford miniature vaporizers we have used, but those things are completely now out of any scientific use. Now this is what is a draw over vaporizer. You can see the patient inspire gas and go inside. This is what is called a draw over vaporizer. EMO and Oxford miniature vaporizer. I am telling you, this is the flow over or bubble through. You can just, these are all not precision vaporizers. Boyle's bottle. Just we can increase from 1 to 3. That's all. On. If you want to, see here, I'm just making it on like this. Now, this is on off. You can also go like this, press the button and make the fluid, the gas bubble through the fluid. That is what you can do. Flow over or bubble through. Both we can do with Boyle's bottle. This is Goldman vaporizer. These are also not precision vaporizers. You can also see 1, 2, 3 and all. So you have to switch it on like this. It just vapors goes out. This is a copper kettle vaporizer. Copper kettle is a measured flow. There is, if you are giving 5 liters gas from the Boyle's machine, there is a splitting ratio. 4 liter goes to the bypass chamber, 1 liter comes down to the vaporizing chamber, takes up the vapor and goes out. This is what is simply happening in a normal vaporizer. What is a measured flow vaporizer? There are two tubes. One is coming directly, bypass. Another is coming regulator. Here you can see here. And then it goes to the vaporizer and both joints. This is what you are keeping a same measured flow of 1 liter. And it goes to the vaporizer and picks up and combines with a separate measured flow, gas flow, and both join and then gives. Now we can already do thermocompensation is supplied heat. Method of vaporization is flow over, bubble through, or injection. I'm not going to this injection vaporizers, which is a separate topic. Single agent or multiple agent. Now what I showed is, in this Goldman vaporizer, we can put halogen also, we can put some ether also. The Boyle's bottle, we can put some, because these are not precision vaporizers. They are multiple agent vaporizers. But what we now have as a single agent vaporizer, if we have sevoflurane, we should fill up only with sevoflurane. That is called single agent vaporizer. Variable bypass or measured flow vaporizers. So this is what is the flow over and the bubble through vaporizers. Now, because the Desflurane vaporizer cannot be controlled by a bimetallic strip, we may need to use a fresh gas separate and the Desflurane is added to a diluted concentration. Now you see there are two gas flows that is equivalent to a measured flow vaporizer. But if you increase the flow, there is some alteration in this in outflow of the vaporizer, so it changes. So it is also a variable bypass. What is this? Desflurane vaporizer Tech6. I will come back again to this small point again after clearly giving the demonstration of the Tech6 vaporizer. Now this is the Tech6 vaporizer. That is the flow meter tube which goes like this, and there is a flow restrictor and this is goes out. Okay. Now if we switch it on here, because this Desflurane vaporizer is under pressure, 2 atmosphere, around 1500 millimeters. What is the normal atmosphere pressure? 760. Inside the vaporizing chamber, the Desflurane is 2 atmospheric pressure. As soon as you open, it will go and then join this here. So this is accounting to the so-called measured flow vaporizer. But if you increase the flow here, this is independent. How the same percentage will come? You set up only 5% Desflurane. If you increase the flow, it will become 4%. So what happens is, here there is a differential pressure transducer. If you increase the flow here, this differential pressure transducer will act and there is a flow increase. That is how the vaporizing chamber is being manipulated by the flow. That is why we call it also as a flow adjusted rather than also a measured flow vaporizer. I am again coming here. You increase the flow here. Precisely controlled. Temperature is there, vapor is there. Now you are giving at some 2 liters. The gas is going like this and it is picking up the Desflurane vapor and going like that. The gaseous Desflurane is going like this. Now take 6. Now you increase the flow. What happens if you increase the flow? Now you see we have increased to 5 liters. What happens is, in 2 liters, it is like this. The circuit resistance. This is what we call is a differential pressure transducer. So if you increase the flow, what happens is, see here the vaporizer, you are increasing the flow. The pressure transducer dome comes up. So now the flow is increased here. So that is how it works. Desflurane vaporizer. There is a differential pressure transducer. Now I am coming again. Now we are putting as 2 liters and the Desflurane concentration is 1%. Now the Desflurane goes and clips. Now if you increase the Desflurane concentration, directly this increases and goes. Now if you increase the flow here, there is a differential pressure transducer which it increases these vapor molecules and adjusts the percentage. That is how this toxic vaporizer works. Again, I am telling here, this is a differential pressure transducer which acts on this and increases the flow if you increase the flow gas. Is a both, now you understand. Now Tech 6 is both a measured flow and a variable bypass vaporizer. What is Tech 5 vaporizer? There is an IPPV assembly. I will come in a different about this pumping effect and pressurizing effect in a different slide. Now if you see, this is the bypass chamber. This is the temperature compensating unit, bimetallic valve. It is down here. And see here, this goes like this. As soon as you this thing valve, the bypass chamber is open, it will go these baffles. This is the wicks and vaporizers and goes out like this and joins the common gas. This is how the Tech 6 vaporizer works. So Tech 5, sorry. Concentration calibrated. Plenum. Vaporizer outside the circuit. Thermocompensator. Flow over. Variable bypass. Agent specific. This is how we should describe a vaporizer. What is Tech 5 vaporizer? It is concentration calibrated. 1%, 2% correctly. It is not chuma like Biles bottle. Plenum, high resistance. When vaporizer is outside the circuit system, it is not inside. It is not inside the circuit. Vaporizer outside the circuit. Thermocompensated. Flow over. Variable bypass. Agent specific. Now there's a bypass chamber is there. There is a bimetallic strip under that down. There is improved response, fluctuating back pressure scale. So we have got a pumping effect of the IPPS. Now what is Tech 7? Tech 7 is similar to Tech 5, but appearance is better and the filling options are different. Now we will go to the Aladdin cassette. Everything is same. Inside is same. There is a splitting chamber, vaporizing chamber, everything is same. But what is the difference is there is a chip which senses and there is a chip which changes the dialed concentration. That is what we are not manually doing it. If you press 2%, the chip changes to 2%. This is the basic difference that becomes from pneumatic to electronic. That is the difference between the routine vaporizer to an electronic vaporizer. It is concentration calibrated. Flow over. The difference is electronically thermocompensated. Works both as a variable bypass and measure. In many ways similar to other variable bypass, but there are several important differences. The vaporizer consists of a bypass chamber. Bypass chamber is in the Boyle's machine and a detachable cassette which serves as a vaporizing chamber. Now we attach a cassette inside, that is a vaporizing chamber. The bypass chamber is already in the Boyle's machine. These two separate parts has to come together when we attach and lock the Aladdin cassette, and this should function as a vaporizer. The liquid anesthetic is filled in front and it goes to the back through a one-way valve. The FGF and the vaporizer output are electronically controlled. That is built inside the anesthesia machine. Now you see, this is concentration control dial. We set up, there is no question of any plus like this. We set up 2% sevoflurane and this comes like this. And the central processing unit, which starts. Now we are not actually doing this. What we are doing is pressing and this is doing this. That is the difference of the Aladdin cassette. And this is also flow restriction. This is the vaporizing chamber. Again, you go there and the same thing, flow restricted valves, all these things bypass. This is VC is vaporizing. Pressure, temperature, everything is sensed. And this senses goes to the CP. Pressure here, temperature here is sensed. And automatically this flow control valve is changed. That is how its temperature is compensated. Or electronic. That is the difference. Now you can see here. This is a locking lever, internal temperature sensing symbol. That is the difference between Aladdin cassette, because it's an exam question. We should be very clear what Aladdin cassette does. Bottle collar. Here you can see here. Bottle adapter and screw that matches the bottle and projections on the collar. We cannot put forane into sorane or something like that. Filler plug and filler receptacle are also indexed for that, color coded for that. All these things we should tell whenever we are writing about vaporizers. So here we can see this vaporizer is this thing, and we can easily, this is a color coded and also index coded. Here we can also fix this only. This is key refilling. We can also do this, and here you can. Quick fill system is this. Press, tuck, like this. This is what is called the quick fill system. But only one vaporizer can be turned on because of the select-tech mechanism. As soon as you switch on the vaporizer, this will tuck like this, and this will not allow this vaporizer to open. Select-tech means is wrong actually. Select a tech vaporizer. Select a tech vaporizer. Tech vaporizer is what? Temperature compensation. This is not technology. Tech vaporizer means Tech 5, Tech 7 means it is temperature compensation. Why do we need all these things? We need safety and no hazards preferably. Now you want to detail a vaporizer? Tech 6, EMO. Concentration calibrated, draw over, variable bypass, thermocompensated, multiple agent, flow over or draw over it may be. This draw over is patient is drawing in. This flow over is not bubble through or anything like that. Vaporizer inside the circuit. Concentration calibrated plenum measured flow VOC agent specific injection. This is how you should describe a Tech 6 vaporizer. Supplied heat outside the system, single agent, injection, plenum, measured flow. All these things should be very clear. What is the method of vaporization? What is the concentration? Is it a plenum? Is it agent specific? What is the type of temperature concentration? Temperature compensation. All these things should be mentioned in a single sentence if we want to describe a vaporizer. There are a lot of hazards with this vaporizer. Now the Desflurane SVP is 664 and boiling point is 23.5. So do we need any wicks or baffles? Nothing is needed. So there are a lot of hazards about vaporizers, physical and all these things, which we'll describe later in the things. Because this itself is going little long. Now critical temperature, latent heat, saturated vapor pressure, boiling point, what is the thermocompensation, what is Tech 5, what is the difference between Tech 5, and how to describe a vaporizer. Thank you all. Visit my YouTube channel, Pain Free Partha, subscribe and share to all friends and encourage us to produce more and more of these video channels.